So welcome to the coding part of this week's video on nonlinear regression. So what we're going to be doing is we're going to be working with near-infrared absorption spectra of the ro-vibrational energy lines of a 12 carbon monoxide molecule. So there's a lot of words in there, but basically what it means is that certain molecules absorb light at certain frequencies depending upon their energy levels. And what we can do is we can look at the individual energy levels there. We can see how the absorption is actually happening, and from that we know how quickly these objects are moving. We know where the absorption spectra should be, so we can tell, given the red or the blue shift of that massive young stellar object, what the velocity of the material that's being absorbed should be at, and check where it is in the spectra. So we can get some idea of the kinematics of these massive young stellar objects. But also, from the equivalent widths of these absorption spectras, we can get rotational temperatures, we can get mass loss rates, assuming certain things. So just from fitting Gaussians to these absorption spectra is the first step of figuring out so much about these objects. And it's amazing that, they're like millions of light years away, and yet by doing such a simple thing, we can understand so much. So we're going to go through that in a moment, but I just wanted to give a bit of background and a bit of context for what we're doing. It's always interesting to think about why you're doing something rather than just to blindly go ahead and do it. So first of all, we're going to have a look at the actual data itself. So it's only very limited as the data that we have, but it's still very interesting nonetheless. And it's in the JSON format, which is something that we've not seen before. So we checked CSV formats before, but now this week we're going to be working with JSON format data. So JSON stands for JavaScript Object Notation, and it's a very simple structure, but it's also very powerful. So we're going to have a look at it, and then we're going to go into the coding part.
So we have here the two JSON files for the two objects that we have. So the massive young stellar objects that we'll be investigating are G223.8 and G263.7. Now we'll only look at fitting one of the spectra here, but you can go ahead and look at the other spectra and the other object in your own leisure. So we're going to have a look at G263.7, and we're actually going to fit the average. So we can see here that this is the JavaScript object notation, the JSON object, and we've essentially got a whole bunch of items here which themselves have arrays of items. So for instance, we have 1, 3, 5, 0, average, 2 and 4. So the average is literally the average of these, and the 0 to 5 here, they're all the different ro-vibrational lines. So they've actually been offset so that you can actually plot them. So they should all have the background of 1, but they don't at the moment because they've been offset for plotting purposes. So we can see that within these objects, labeled 1, 2, 3, etc., there are X and Y objects, and these objects themselves are arrays of numbers. So X are literally X values and Y are Y values as you would plot them on an XY scatter plot. So the X values in this correspond to an actual velocity. We know where the lines should be, we know where the velocity of the object in space is, so we know how far it should be redshifted or shouldn't be. So we can then actually plot everything as a space velocity compared to the object rather than as a wavelength. So what we're going to do is we're going to read this in, and we're going to extract the average and then the X and Y from this. So now we've got a basic understanding of the JSON object structure. We're going to start the coding. So we've seen that we've got our data in a JSON format, and what we're going to do first is we're going to reuse the notebook that we created in the last video. So because a lot of that structure, a lot of that architecture that we had, we're going to just reuse. But you can see here in the preamble, I've actually wrote out the equations of the nonlinear inversion, as well as here we've got y. This is the function that we're wanting to fit. So we've got 1, that should be the background of these spectra, and we know that because that's how it was acquired. And then the absorption spectra is a lack of something, a lack of light in that frequency hitting the detector. So we should actually have an inverted Gaussian, so hence it's 1 minus a Gaussian function. What I've then gone ahead and done is write the derivatives of that Gaussian or that y function with respect to all the model parameters. So dy by dA, dy by dx bar. X bar here is just the average, so the center of that Gaussian, and then dy by d sigma, where sigma is the proxy for the width. So what we're going to do is we don't need this NumPy, this pandas package anymore, because we're going to use a different package because we're reading in JSONs now rather than CSV that we did in the last lesson. So I'm going to replace this with a package called JSON. Funnily enough, there is a package called JSON to read in JSON files. So going down here, what else are we going to have to change? Well, we're going to have to completely change this make G function, because the G here is actually going to be the J term here. So that's going to be a matrix, which is going to be the number of samples, so the length of X essentially, by 3. We're going to have 3 model parameters, so hence 3 columns. So what we can actually do is take out these 2 lines, and when we've got here polynomial degree plus 1, we can just replace that with 3, because we know we're going to need 3. So we'll remove the polynomial degree from the call to the function as well. So this reading in of the function, this is really where most of the difference is going to come in. So what we're going to want to do is we're going to want to open this particular file. So we've got 2 of those files that we saw already. So one of them was called G263.7 JSON. And then we can do with open whatever this file is called. So we're just going to create a pointer to this object, pointer to this file, and then open it with json.load and just that file handle, and I'm going to store it in something called JS. So what JS will be now is a dictionary. So JSONs can be read in essentially as dictionaries. So I'm going to have another cell below that, and because I want to separate off the different sections. So when I want to read data in, I want that as one section, pre-processing another section. So what I'm actually going to do is, because I know that the background should be 1, I'm actually going to pre-process this data such that the background is always 1. And I know that there are multiple lines in each JSON, so I'm going to actually loop through each line. So I'm going to say for key in JS, so we know that JS is a dictionary because that's how the JSONs are read in. So each key in there, as we saw from the JSON, is actually going to be the absorption line or the average. And then I want to basically set that background to be 1, or at least, an average of 1. And I only want it for the y terms because the x is just, the space velocity in this case, but it's a proxy for wavelength. So what I can do there is I can use a NumPy package and the median function. So I can say that this y value should be equal to whatever that y value is minus the median of it. So if the background was 0.8, I can subtract 0.8 and then just add 1. So then the median should then become 1. There we go. So that's doing a bit of pre-processing. So I want to insert another cell, and here I want to just plot the data and just look at it, because it's always good to just look at the data. So we saw the actual JSON format, but we didn't see what the data looked like. So I'm going to extract an X and a Y here, because I'm only going to deal with fitting one of these lines at once. So I'm just going to take the average. So obviously this is going to be the average X, and Y is going to be the average Y. So now I've got X and Y, it's just going to be a simple matter of plotting them. So plot X, Y, and have each individual point as an X. So if I run just the import and these other statements, although it should pretty much work because I've not actually changed anything such that it will fail, we can see here, this is what the spectra looks like for, which one is this? G263.7, and this is the average. So we can see it's not quite a Gaussian. We can see here we've got, you know, a big spike here, which probably looks like a very narrow Gaussian, and then, you know, a more broader one. So there's probably a couple in here that we could actually fit, but we're just going to fit one and see what happens. So what we need to do is we need to define an initial model, M. So we can just guess these values. So we could look at this and go, well, I think that the center might be around 20 and the width might be around 10, etc. But we can be a bit more intelligent about how we go about doing this. So we know that the three model values that we are after are the amplitude, the central point, and the standard deviation. So for the amplitude, we can just take what the minimum value is and then subtract that from 1, because, you know, we're looking for basically this depth here. And again, for the central point, we could just take, well, what is the central point of that minimum? So we can be a bit more intelligent about how we do these things. So I can look for an index which is going to be the minimum of this y value, and then the amplitude is going to be what that y value is at that minimum, but 1 minus it. And then the central location is going to be whereabouts in the x value that minimum occurs. And we could possibly do something a bit fancier for the width, but for this instance I'm just going to guess it and just say 5 and just hope that that's a good guess. So a lot of this we need to rewrite as well. So we need to basically loop around, because you see here we have a loop. So we iterate over the model parameters. So we need to loop over and update the model parameters and then add that back to M. So we're going to have, I'm going to say a variable called n epochs, which is going to specify how many loops I'm going to have. And I'm just going to set that to 10 to begin with. I don't want it to be too fancy and out there. So I'm going to say for iteration in range n epochs, so that will give me a loop over all of these. And what I need is I need my residual values, which I get from my current estimate of the model parameters, and I also need to have j at the current model parameters, so this Jacobian matrix. So we can do that pretty easily. So let's go back down to our loop. So we need an estimate of what our observable y values are given the current model. So I'm just going to call that y hat, and I'm going to say that there's going to be some kind of function called forward model that will give me y hat. So the residuals are then basically y hat minus y, that way. And then I'm going to call this linear inversion with this residual as the y value and the x value and some lambda. So let's go ahead and say, what was that called? Linear inversion. Okay, so linear inversion, and it's going to get called with the x value, the residual, and some lambda. I'm not going to call it lambda, I'm just going to call it lam, because obviously lambda is a reserved variable name. So we're going to say, well, we might want to use it in the future, so we want to keep the ability to make lambda functions. So I'm going to say that it's 0 to begin with, just to see what happens. So this is going to be the update for the model, so it's going to be dm, and then we're going to have to subtract that from the current model to then get our new model. So then m equals m, I can say minus equals dm. And then what I might also want to do is again print out some costs, print out some image of what the model looks like. So I'm going to have a couple of plots. So I'm going to plot what the data is, x and y, and also plot what the current model looks like. So I'm going to have x and y hat, and I'm then going to use plot.show so it puts different plots down rather than rewriting them onto the same image. And I'm going to also want some print statements for the costs, so I'm going to use get cost. Well, we don't actually need get cost because we've actually got the residuals here, so we've had to generate the residuals, so we don't need the get cost function. We can just print the norm of these residuals. And I also want the norm of the model as well to see how the model is changing per iteration. So I'm going to have a formatted string, and I'm just going to say I'm going to have the data norm. So the good thing about formatted strings is that you can write it as you would see it rather than having to put placeholders in that you later come back to. And I'm going to have model norm as well. And this is just going to be the exact same thing, a second order norm, but I'm going to do this on DM. So what is the current change in the model parameters? So I don't need any of this anymore. But what I do need is to implement this forward model function, which I can intuitively think of is actually going to need the x and the current model. And then also going to redo this make g function, which I can also see is going to need to take the model parameters as well. So let's start off with the forward model, because that's going to actually be very simple to implement. So we're going to need a function called forward model. I've already said it's going to take x and the model parameters, and all I need to do is form this equation. So I'm going to return y, and y is going to be what I'm going to generate in here, but I'm going to call it y hat because really it is just an estimate. So y hat is going to be 1, obviously, we've got a 1 in that equation, and it's minus the amplitude, which is going to be the first model parameter, m0, and it's going to be times by an exponential, and it's going to be x minus x bar, which is the second model parameter, all squared. So we're going to have x minus x, oh no, sorry, not x, m1, and that is going to be all squared, and I'm going to use the numpy power function for that, and I'm going to square it, and there should be a negative there as well, and we're going to divide that by 2 times np dot power of m2 raised to the power of 2. So this is actually going to be very useful because I'm going to need this when I'm calculating all of these derivatives as well. This exponential is going to stay the same, so this is going to be an interesting little parameter that I need to, or coding string that I'll need to keep. So let me just check this is okay. Yep. So I might actually change that to np.exponential as well. So there's a lot of brackets here, so I'm just going to make sure that they're all in place. So there we go, we just needed one more bracket. So now we need to make this g function, and I already said this exponential we're going to have to copy over because it's going to be reused in everything, so I'm actually just going to store it as a variable and say that the exponent is equal to this. So the first derivative is, which is essentially going to be the first column, is just the negative of that exponent. So the first column is just negative of the exponent. The second column is minus a times x minus x bar over sigma squared times that exponent. So that's minus m0 multiplied by this bracket times the exponent and divided by sigma squared. So I'm going to need this bit here. So then all we need to do is the next column, the last column, which is minus ax minus x bar squared over sigma cubed. So this is essentially everything that's in this exponent. So I can take the entire thing out. I don't need the negative term. Well, I do, but I need to times that by m0. And then this is also going to be a cubed, and there is no 2. And then that needs to be times by the exponent. But just for personal quirk, I'm going to move this to the end. That just looks a bit better for me. Okay, so I think that is all ready to go now. So it's just a matter of running this, and hopefully there isn't any problems. We've already loaded our data in, so it's just a matter of forming this initial model parameter. Okay, that works fine. And then running this loop. We can see we have a problem here that we didn't run this. So let's run that again. And then hopefully this time it will work. We have another problem. A list and float. So what we have is our x and y in a list value, and we can't just do mathematical operations on lists. So what we do need to do is transform them into numpy arrays. So we can do that with the numpy.array function. So we'll do that, and hopefully, yep, still plots okay. So let's run that again. And yes, I did say that I was going to put a lambda in there, plus there doesn't need to be a polynomial degree. And yep, the make g needs to be changed. So there's a lot we missed out here. So this is common. You just have to go back and make sure what you're doing is correct. So again, we don't need polynomial degree here. That's just going to be 3. So I think that should be okay. Let's try that again. Okay. Yes, I didn't pass m in. Okay. So a linear inversion requires m, of course. Here we go. So here is the first Gaussian that was fit. And we see a data norm for that and a model norm. And we can hopefully see that, yep, the data norm is reducing. I'm not quite bothered about the model norm. If that increases, then that's fine. That's just saying that it's a large change in the model. If it gets out of hand, then it might be something to consider. So although it has a very good fit to this initial peak, it's actually not the majority of the data. So it's still trying to reduce the residual as much as possible. So you can see it's moving towards the center of this large mass rather than that small particular peak. And we can see that the data norm is actually reducing, so we're getting down to 1.2 now, and we can see that this is getting to recover most of the data, and the model norm is actually reducing quite a bit now, so it's less than 1. So actually the changes are not large, and again 0.2, 0.07. So at this point the model isn't really changing very much at all, and you can see that in the data norm. You've gone from 1.1536 to 1.1536. There is basically no change in the data norm. So one of the things that we can do is, if we don't want to specify a number of epochs, we can specify a particular stopping criteria. So we can say if this data norm here minus a previous data norm, so I can say norm history, I can say if the absolute value of that is tiny, so let's say less than 0.01, then break, so it'll exit that loop. So now I can set epochs to whatever I want, and hopefully it should keep doing that. We'll of course need to store norm history, so I'll probably have an else statement there and say norm history equals this actual value. And there's going to be a problem here that norm history doesn't exist on the first one. So we're just going to put up here norm history equal to 0, because if the model's a perfect fit, then the normalization is 0, and if it's close to 0, yes, we want to break anyway. So we can see that that stopped immediately on the first iteration because we're starting off from where we finished, and we saw that the data norm wasn't reducing very much at all. So that's pretty much everything I want to cover in this section. So one of the things we can do to clean up is actually get rid of a lot of these functions that we don't need. So we didn't need the get cost function. We didn't need the plotting function up here. So realistically, this is all we needed to plot Gaussian functions to these infrared spectra.
So hopefully you enjoyed that and it was very informative for you. So as always, we're going to have a link in the description to the GitHub repository that will include not only the data but also the notebook that we've used in this practical. So next week we're going to be having a look at including the data and model covariance matrices into the actual inversion schemes that we've done already. So this is going to be quite interesting because, as we all know, there's some correlation between certain model parameters, but more importantly, there's different data points have different errors associated with them. If we have a bunch of data stretching back from the 1960 to the present day, the data that was acquired in 1960 might not necessarily be as accurate as that in the present day. So we want to weight it as such. So we're going to see how we can actually incorporate that into our inversion schemes in the next lesson. So hopefully I'll see you then. And if you like this video, please click like and subscribe and hit that little bell icon so you can be notified when we do upload new videos. Thanks for watching.